right in the center. And that's a nice right circular cylinder. And what they want to know is what's the volume of the shaded area, which is everything but the cylinder. Okay. So we've got two types of geometric shapes here. We've got the box itself, the cube. So we want the volume of the cube. But we also have the cylinder, and I'll just call that CYL. Okay. This is 5 inches on the side. So the volume of the cube would simply be this one right up here, S cubed. So we make that 5 cubed, because that's what S is. And the cylinder, the formula for the cylinder is right here, pi r squared h, which let's say is 3.14 for pi. Now the radius they have to give us, and that radius is 1 inch. Okay, so the r squared would just be 1 squared. And the h is the same as the cube itself, because it goes all the way through. So that's going to be 5. Well, 5 cubed is, anyone know the cubes? Memorize cube formulas? It's 5 times 25, which is 125. And this would be cubic inches. In math, we would write it that way, inch with a little exponent of 3.
Is this review from the homework, or is this new formulas that you're teaching? Is this from the homework?
This is a homework, yeah. This is number, which one?
41.
41. Okay, so we have this 3.14. 1 squared, of course, is 1 times 5 is 5. So we have to multiply that out on our calculator. This becomes 15.7, and that would be inches cubed. So that's the volume of the whole. The volume of the entire cube itself, including the whole, is 125 cubic inches. So we need to subtract the volume of the cylinder from the whole, from the entire cube. So it's V for the cube minus V for the cylinder, which is going to be 125 minus 15.7. And I get 109.3, and that would be cubic inches. Now that's using 3.14 for pi, which is usually acceptable. Any other questions on the homework?
35?
25?
35.
35.
On that one, is that in all scenarios? I mean, like, because how would you know enough to add together?
Well, it's because
You know,
when you use this formula, the formula for the cube, you're getting the entire thing, including the whole. So you're getting too much, because they want to know what is the region excluding the whole. So what you do is figure out the whole volume, which in this case is 15.7 cubic inches, and subtract it from the entire thing. And that gives you the result. A situation where you would add would be something like having a cube and then taking that cylinder, maybe putting it on top of the cube and saying, I want the volume of the cube and plus the cylinder, then you would add.
but anytime it's inside, it's taken away.
Yeah, you do a takeaway. Yeah, exactly. Okay. 35, huh? Okay, we have something that looks like a big medicine pill here. But it turns out it's a storage tank. It looks something like this. And it's got sort of a semicircle, or actually half of a sphere on both ends. This is 9 feet. And the diameter of the circular part over here is 2 feet. That's this distance here. And again, they want the total volume. Okay, now this is half of the sphere here, and the other half is over here. So we've got one total sphere of the diameter, 2 feet. So we want volume of a cylinder, because that's this part, the middle part. And to that, we want to add the volume of the sphere. Okay, the cylinder, once again, is pi r squared h, so we'll take 3.14 for pi. The radius, now we get the radius by going over here, because the radius of that cylinder would be that distance, which is exactly half of the one they gave us. That's the diameter. So the radius would be 1/2 of that, which is 1 foot. So pi r squared would be pi times 1 squared, times the length is going to be 90. So that's going to end up being 9 times 3.14. Now the volume of the sphere, sitting over there, 4/3 pi 3.14 r cubed. And the r in this case is the same r, it's at 1 foot. Okay, so now we have to figure out the numbers and go from there. So 9 times 3.14.
Isn't it's a hemisphere, so it's half the sphere, so it's like half times 4/3.
Yeah, but you got two hemispheres. If you take two hemispheres and put them together, you get one sphere. So all you need is the sphere formula. Yeah. And this turns out to be, I get 28.26 cubic inches. Now that's just the cylindrical part here. Okay? Then you add the sphere on both sides. So that's going to be 4/3 times 3.14. Let's talk about how you would enter that into the calculator, just so everyone knows that they can do it in a certain way.
Okay.
The button pushes for this would be 4, of course, times 3.14. Now, you want to divide the entire thing by 3. Probably the safest way to do this is use your parentheses. And that way the calculator cannot possibly make a mistake. So what I would do is open a parentheses here and close a parentheses over here, saying I want that taken as one single calculation. Remember, parentheses to a calculator mean the same thing that they do to us in PEMDAS. Okay? Do me first. So you're saying you're forcing the calculators to make that one calculation before it does this calculation. That would be the divide calculation by 3. And then you say, okay, I'm done, give me an answer. Okay? So just putting in those parentheses ensures that you're going to get the right answer. If you don't put in the parentheses, in this particular case, you probably will still get the right answer. But if you had a sum of two things here, you would not get the right answer. So at that point, parentheses have to be used. So you have to be careful. Okay, so let's see what this is. For this, I get 4.18, and then that's a repeater. So if we go out to the hundredths position, this would be approximately 4.19, and this would be cubic inches. Okay. So what do we have here? We've got the cylinder, which is this much, and we've got the two caps, which amount to a sphere, which is this much. So let's put those two together. And the total thing comes out to be 32.45. If you go out to this and round it to that position, it's 32.45, and that would be cubic inches. Okay, any others? Yes.
On this thing, the 4/3, you're just timesing it 4 by 3.
Yeah, I'm just doing it that way. You don't have to.
Well, what about the other third? I mean, it's 4/3.
Right. So I'm multiplying the 4 by the 3.14. That happens right. Happens right there. Okay. But then I've got to divide that whole thing by 3.
Does that 3 relate to the
And there's
third part of?
Yeah, that's the 3 down here.
Ah, so if that was a fifth, you'd divide it by 5.
Yeah.
Okay.
Yeah, whatever the denominator is.
Okay.
But what I'm saying is, when you're doing it this way, you should tell the calculator to do this first, 4 times 3.14, then divide by 3. As I say, in this particular case, because you're multiplying, you're not really taking a chance.
Could you take the 4/3 and turn it to a decimal?
You can do that. You can take 4/3, and of course that would be a
Divide, yeah.
repeater,
Right,
you know, because it's a third.
right.
So
Yeah.
you get a repeater up here,
Mm.
and then you multiply by 3.14. Yeah, you can do it that way. That's fine.
The book also has just 32 feet
Yeah, it's
square.
because they
I
didn't
mean,
use
cube.
as accurate
Yeah.
measurement over here. I chopped off, I rounded that off.
Okay.
This is a repeater over here, so I rounded it off to 4.19.
Okay.
Yeah.
At the beginning of objective 2, when we do the volume formulas for selected solids, it says find the volume and use 3.14 for pi where necessary. And I wasn't sure how to determine where it was necessary.
What they're saying is, if they don't tell you in a particular problem what to use for pi, then use 3.14. Yeah. That's the standard thing to use. And the reason why they're doing that is because some people don't have calculators. If you have a calculator with a pi button, of course use it. You know, get much more accuracy if you do that. But some people don't have that. Any other questions on homework? Yeah. Number 9? All right. It says, determine the area of the square and the volume of the cube. So first of all, you have a two-dimensional object that is a square, and it's got 1 foot here, and that's all it's got. And then they take that two-dimensional object of the square and sort of move it back into a different dimension like this, and they create a cube. Actually, that's all a cube is. It's a square that's been moved in one direction. And this has a side of 1 foot also. Okay, so the area for this one is simply length times width, very much like a rectangle, but they're both the same. They're both 1 foot because it's a square. So it's 1 times 1, which is 1 square foot. Okay, but here, because it's a cube, this would be 1 foot, and this would also be 1 foot. So the volume for that is s cubed, which is going to be 1 times 1 times 1, which also equals 1, but it's cubic feet. It's cubic feet, this is square feet. Okay? This is a measure of volume, this is a measure of area. So area always comes out with square somethings, square inches, square centimeters, whatever, and volume always comes out with cubic. Okay? So, you know, people say, well, can't I just get the numerical answer? Actually, if you're going to be hired by a company, they don't want just a numerical answer, they want the units also. You know, this is the problem that happened. Remember I told you that story about the Mars lander? Okay, $500 million on the surface of Mars right now that we'll never use, and it's your tax money, and it happened because different units were used. No one talked about the guys over there in France making that part, and the guys over here in Idaho making this part. They use different units, you know? So, yeah, putting this stuff down in an answer is what, or not doing that is what cost us $500 million. Yeah. So you gotta do it. Any others in here? Okay. We go on to section 9. Chapter 9. And chapter 9 is basically a very mild introduction to statistics. Now, what is statistics? Well, an awful lot of work is done, especially by your government, to analyze, organize, and collect data. Now, first of all, let's be good math students. The word data is a plural word. Okay? Meaning data means more than one. Data is many measurements. It's not just from Star Trek. Okay? If you want to talk about one measurement, there's a singular. This is all Latin. And the singular for that is datum. But no one ever uses that. But that will, you know, that will keep you up to date and acceptable at cocktail parties. Okay. All right, what we want to do is statistics. Let's do a definition of it. Collect, organize, and analyze data. That's what it does. And some parts of that process are pretty easy, and other parts are not so easy. We do have a course in statistics here. I think some of you probably are scheduled to take it. I'm not sure, but you have to check your own, go to the counselor like Suzanne and find out what your schedule is to take. Okay. Today, we're going to look at two parts of this, organize and collect. The analyze involves formulas. Some of those formulas are kind of esoteric, and we're not going to do them in our course. We'll do them in some other statistics course. All right, now what kind of data do we usually get? In other words, if you're collecting data, what kind are you getting? Well, we could, let's say, take a class member and send them out into that parking lot. This is, by the way, a staff-only parking lot. Big one out here. Okay. Let me see the parking in there. All right. All right. But you could go out there and you could sit there, from 8 o'clock in the morning on, and actually keep some records. Okay, here's a female driver, and the female driver came in an SUV. Okay. Male driver comes in a truck, and so forth and so on. All right. The kind of data you'd be collecting there is what's called whole numbers or integers, because, is for every one person you get one particular type of vehicle, and you could have maybe even, motorcycles. I guess there's some people who park their motorcycle out there, and so forth. And that we'll have a problem like that. We'll look at a problem like that in just a minute. So basically, you're counting whole numbers, and that's very simple kind of data. But honestly, most of the data that's taken in the world today is not done that way. It's done on devices which are fundamentally not too different from this. It's a calculator which is decimal based. So some data might have to do with the width of the parking lot as it goes from one end to the other. Well, you're going to use a machine that sends out a little beam, maybe a radio beam or something like that. It comes back and measures the distance very, very accurately as a decimal number. Okay? So most data in the world is done with decimals. Okay? But that still is a bunch of numbers. So collecting data is simply accumulating. Spell that right. Accumulating numbers. Now, your government does a huge amount of this. They, there's a census, every 4 or 5 years, something like that. That's how they redistrict Congress. If population shifts, then this particular section gets more Congress people, and so forth and so on. So they accumulate lots of data. Once that data has been accumulated, the most important thing is how you present it to other people. Because most people do not like tables. We're going to look at tables to begin with. They're not that bad. But, you get a person over 35 years old looking at a table, and I know what it does for me is put me to sleep. I'm gone. I don't like tables. Which is ridiculous because I teach mathematics, right? But I don't like tables. All right. So you got to do something to organize it, which also means present. So I'll put that up here too. You want to present the data in a nice way. So your job's not really done until you do that. Analyze is a different thing. Analyze has to do with taking the statistics course and figuring out what the average data is. If we talked about, let's say, the average age of members of this class, we'd have to have a formula to do that. We'd have to go to some algebra to do that. So that's a different course, and we're not going to deal too much with that. All right, so let's take a look at some examples here. We're on page 530. I hope you can look on if you don't have your book. There's a table there. So the table is the very first way we're going to look at organizing data. Now this table has a huge amount of data in it, and that's the advantage of a table. It says, it summarizes the maximum wind speed, number of reported deaths, and estimated cost for recent hurricanes that made landfall in the United States. And yeah, there they are. There's Katrina, Fran, Andrew, and so forth. Some of them a long time ago. But notice, a table is a mini spreadsheet. Okay? Mini spreadsheet. And what that means is it's got rows and columns. Okay, that's the definition of a table. Rows and columns. Okay, now columns are vertical. Rows are horizontal. So what you get is really a section of an Excel spreadsheet. That's all it is. If you've ever worked with that on a computer, you know what it is. So it's a rectangular box that's been split into many little sub-boxes. So you've got this kind of an arrangement. There's the columns. Here come the rows. And the purpose of all this is organization. So the data is readable. Now this is a step up from what's called raw data. Okay, raw data is just a bunch of numbers sitting there, and someone has to actually organize it like this. In this particular case, I'll just put a few of the column labels on it and so forth. This is the, let's go over here and do the hurricane. That's the actual name of the hurricane. And you've got the date. And you've got where it made landfall. And maximum wind speed, number of deaths, and so forth. There's a huge amount of data here. And we've put another one over here just to get the last one in, cost. And then you've got the name here. This is Katrina, and Fran, and Andrew, and so forth. Hugo, and there's actually another one, but we're just going to look at a certain portion of it. All right, now notice when you have columns and rows, you form these little sub boxes, and those smaller boxes are where you put the actual numbers, and those are called cells. So this is known as a cell, and there's a lot of cells in there. So the dates, for example, Katrina was 2005, and Fran 1996, 1992 for Andrew, and 1989 for Hugo. Okay, where it made landfall, different places, of course. And the maximum wind speeds, I'm just going to put some of the numerical data in there. 125 for Katrina, 115 for Fran, 145 for Andrew, and 130 for Hugo. And I'm going to skip over to the cost column now. The cost for Katrina was $81.2 billion. That's a lot of money. Fran, 5.8 billion. Andrew, 35.6 billion. And this one, 10.8. Now, it's kind of interesting here. One thing, if you look at it, just stare at that for a while, something's going to jump out. And what jumps out is, well, Katrina, which did by far the most damage, 81.2 billion, did not have the highest wind speed. Andrew did, much less. Why? Where did it make landfall, right? Katrina made landfall in an extremely populated area, Louisiana. And Andrew, Florida, and partially in Louisiana, but nowhere near as populated. So, reading tables, it's possible to get some information that you need out of it just by looking at it. But you do have to sit there and stare at them and realize that you locate a particular cell by the row and column headings. For example, if you're interested in Hugo and you want the cost of Hugo, you start with Hugo, go across until you get to cost. The intersection of Hugo and cost is 10.8. Here's your number. So that's the way you use a table. You locate the data by going horizontally, vertically, and the order doesn't matter. You can go vertical and then horizontal. Okay, so you can get information. And as I say, there's lots of information here. You have 1, 2, 3, 4, 5 columns, and actually 5 hurricanes also. So there's a lot of information in that one table. They ask a few questions. Which hurricane caused the greatest number of deaths? And that's, very obvious. It's Katrina, 1,836, and so forth. That's considered to be a way of presenting data that would be good for technical people or people who maybe are working behind the scenes in a corporation. That's a presentation that works. People who are used to reading tables, it's okay. But when you get to, let's say, talking to the bosses of the corporation at a board meeting, and you want to present that same data, you better not put a table in front, because they're not going to like it. They want it to be pretty, and they can just take one glance, and they can see what's the fastest wind speed without, having to go rows and columns. They don't want to do that. That's your job, not theirs. I mean, really, that's the way it is today. So, what we'll do is take some time to construct a table, and so you'll know how you go from raw data into the table form, and then we'll immediately go from tables into something much more readable and presentable. Again, on page 531, following data were taken by a student conducting a study for a statistics class. The student observed the type of vehicle and gender of the driver for 18 vehicles in the school parking lot. Complete the table. Now, first of all, you'll notice that what they do is construct a table that's much smaller than the hurricane one. It's got basically 3 rows, and only 2 of them have to do with the gender. This is the male row, this is the female row. This is split up into 2 labels. The horizontal label is the driver, and this is the vehicle going across, which is kind of unusual to do it that way. And they have 3 types of vehicles: car, truck, and motorcycle. Okay, the raw data is up there. It's right above that. And what it says is male car, female car, female motorcycle, and so forth and so on. That's the raw data. That's what someone sitting outside would actually write down on a pad of paper. Okay? That and $3 gets you a cup of coffee. Nobody's interested in raw data. They're not going to pay you a cent for that. Okay? They're going to pay you to take that and massage it and make it look pretty. That's what you get paid for. Okay? So here's how you do it. They take one of these boxes like this, and they start putting in what they call them a tally mark. They go through there, and every time they find one category, male car, and they say, yeah, the first measurement was that, male car, they put a tally mark. And they keep going through and so forth. Are there any more male cars? Yeah, there's one down there, a little further down, and there's 2, 3, 2 more. Okay, and that's it. All right, then male truck. Okay, let's go through again. One here. See, this is time consuming. And that's what they're paying you for, to consume time. And so forth. So you get the tally marks. And again, they don't want to see tally marks. Do not give the boss tally marks. Okay? Go back and change it into some numbers. They don't know what you're talking about with tally marks. They want to see numbers. So eventually, you're going to have to go through this whole thing and write a 4 there. They know what a 4 is, and I think it's about a 5 here or something like that. So you're going to have to convert it to regular whole numbers. And finally, you get down to a table that they're willing to look at maybe. It's called Table 9-2. Okay. That's how you go to one of these tables. Now, what we're going to do is go back to the hurricane one and make it pretty. Now, the first thing you'll notice in making it pretty is that we're going to have to cut down severely on the amount of data we present, okay? Because that table has far too much in it. And on page 532, they give what's called a bar graph. And bar graphs are one of those popular ways of presenting data. This is what they're going to pay you to do, bar graph. It is actually a table, but various columns in the table will be expressed by the height of bars. Now, I'm going to sketch this one up here because your book doesn't do a good job of describing how to do this. So we're going to make it a little bit more interesting. A bar graph has a horizontal axis and a vertical axis. And they are for different things. What they decided to do in this particular case is to show the wind speed for the hurricanes listed. All right. So what they did is create a vertical axis which will cover the wind speeds of these hurricanes. So you go over here and you say, well, the highest one's 145, the least one looks about 115. There was one more hurricane in there, let's just check that. That was Alicia, and the wind speed was again 115. So you need to have the ability to go between 115 and 145 over here. And you want to do it in such a way that you create a scale that's what's called linear. You don't want the separation between 2 points on the scale to change. You want it to remain the same. So you're going to take that difference between 145 and 115, which is 30, and divide it up into several segments that are equal spacing. And they started to do it this way. They started at 0 because they're doing a bar graph. If you were doing a different kind of graph, you might not start at 0. But they started at 0, and they decided to bring it up all the way to 160, and the difference between the two marks is always 20. Now this is their decision, and it's a decision you would make if you were creating a table on a bar graph. So this is 0, this is 20 miles per hour, and this is 40, and so forth. And the spacing, as I say, has got to be equal. 80, 100. Now we're starting to get up in the area where we actually get some real data. This is 120, this is 140, and so forth, 160, and that's it. We don't need to go any further than that. So they chose this spacing so that the actual tops of the bars are going to be in this range right here. See, if you have bars that are, the tops are down here, everyone says, why are they so short? Believe it or not, people have an inherent sense of what's proportional and right. And if you have all your bars down over here, they're going to say, oh, they're too short. I can't really see the difference in the bars. You know, they want them up higher. So this actually will work very well. The next thing is you have all the hurricanes. You've got to list all the hurricanes. Now they started with Katrina first and then go down to Alicia. That's just a choice. You don't have to do that. So the very first one is Katrina, and then we have Fran, and so forth. Andrew. Now, in order to make it look pretty, what you want to do is space the bars evenly, okay? Now, the names, of course, are different width, but when you make a bar for that name, then the next one's going to be a certain distance, and the same distance for the next one, the same distance apart, okay? So let's say we put Katrina here. We want the distance to Fran to be there. We want the distance to Andrew to be the same, Hugo the same, and Alicia the same. So that's going to be the center of our bar for each one of these particular hurricanes. All right, for Katrina, which ends with an A, we've got 125 miles an hour. So I'm going to center a bar on that little mark down there that goes up to 125, which should be right about there. And then you create a vertical bar around that mark. And you put your top across. If you want to be real nice to people, you know, so that they don't have to strain their brains too much, you put the number that you're trying to describe on the top of the bar. So you write, this is 125. Okay? That way they don't have to say, well, what is that, 129 or 125? Okay. The next one is Fran, that's 115 and so forth. And you want the spacing to be the same between them, and you also want the spacing of the bar to be equal all the way across. So 115 will go up to about here. You want it to have a nice kind of symmetry to it. Andrew is the big one, it's 145. And so Andrew will go from 0 to 145, which is about up here. And of course, you can put the others on. And it'll be easy. This is 115, this is 145. It'll be easy for them to see, Andrew had the greatest wind speed. Now notice what we're losing here. We're losing information about a lot of things. The date, where it made landfall, the cost, number of deaths, it's not on here. We're only showing a relationship between a particular hurricane and the wind speed of landfall. That's it. So there's a disadvantage to going to a bar. The advantage is it's really easy to read. I mean, kids could look at it and probably figure it out real quick. So that means bosses probably could. Yeah. Now, if you look down right below that, on page 532, you've got another bar graph, and this is a horizontal bar graph. The bars here that we just did are vertical. These are horizontal. And notice they choose two colors of bars. And what is that to represent? It's to represent the table we just had up there about the cars in the parking lot. Male, female, car, truck, motorcycle. And what they decided to do is put the numbers of the tally marks on the horizontal axis and a description of the vehicle over here on the vertical axis, motorcycle, truck, car. The color represents the gender. So that actually gives them more ability to present data because they're using the color. The color determines the gender. Blue is male, pink is female. So for example, you can say motorcycle, okay, 1 female, 2 males. Got it right away. You can read it very quickly, huh? Horizontal is perfectly okay. Horizontal bar graph is considered fine. One point I want to make about doing all this stuff is when you do a bar graph, you should always label it. For example, here they label this wind speed at landfall. This should be labeled over here as MPH, miles per hour. And this, of course, you don't really have to label because it's obviously the name of the hurricanes. Does anyone read the newspaper USA Today? It's the only national newspaper we have. You know, they love bar graphs, and they love all sorts of charts and stuff like that. Every single page has it, right? And they do them terribly.
Yeah.
Absolutely terrible.
Yeah.
Because sometimes they don't even label them. You've got a graph there, and is it furlongs per fortnight? I mean, you have no idea what it is, right? Nobody knows. You've got to read the article to figure out what the graph is. Well, the whole point of a graph is so you won't have to read the article. You know, come on. New York Times, LA Times, they do it perfectly. Everything's labeled right. Huh? They've got people who know what they're doing. So, equal spacing between bars, equal width of bars. Looks pretty then. And the action of this bar graph is occurring up here, not down there, up here. In other words, make the bars come up a bit so they can see differences in height and so forth. Putting them down here, so, you know, are you being cheap with ink or something? You know, people think something's wrong. So there's aesthetics here. Part of presenting data is make it aesthetically pleasing. So they get it and they like it. Then they pay a lot of money. One other thing. In this horizontal one, which is on page 532, a motorcycle, car, truck. Notice there's something in the graph itself. There's this little box which shows you pink for female and blue for male. That's called a legend. Okay, a legend is providing the information which may be perfectly obvious to most people, but you still provide it to be complete. Okay, so they can interpret what you're doing. You know, you're doing this to give people who don't normally work with data information quickly and in a way they can't mistake. So give them a legend. You know, putting that in makes it much easier to read. All right, so let's shift over to the next topic, which actually is still a form of bar graph. It's called a pictograph. Oh, I don't want to skip this one. This one down at the bottom here, 532. I've got to tell you this because I feel obligated to provide this information for your health. It's about the number of fat grams for 5 different ice cream brands and flavors. They're half-cup servings. Now, nobody eats a half a cup of ice cream. Got it? Right. We eat 3 or 4 cups, you know, not a half a cup. All right, so you go from Breyer's strawberry, Edie's Grand Light Mint, Healthy Choice, Ben & Jerry's chocolate chip, and Haagen-Dazs. Haagen-Dazs, remember, is not made in Holland. It is made in New Jersey. And the reason why you like it so much is it has tons of fat, not a little bit. And you can, this is a table, of course, and you can read the table, but it's nowhere near as dramatic as going over to the next page and looking at the bar graph. Now, this is a bar graph constructed just the way we did ours, huh? Okay, so you find that Breyer's 6 grams, Edie's 4.5, Healthy Choice 2 grams of fat in half a cup. Obviously. Oh, there's Haagen-Dazs, 20 grams of fat in half a cup. Need I say more? Okay. Yeah, change your brand. All right, pictographs, next page. Now, this is a kind of fun thing because what they do is instead of making bars, vertical bars, which are kind of boring, they make stacks of icons. And the icon represents some number of something. In this case, the number of music CDs sold in the United States is given by this figure. Right? What is the value of each CD icon on the graph? They use a little tiny CD. Okay, I know CDs aren't used anymore, but just, you know, be patient. It looks like in 2003 and 1999, that's where they sold the most CDs. They're in millions. So in 2003, they sold, well, it looks to me like about 950 million CDs. It says 1 CD is equal to 100 million. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, and then half of another one, about 950 million CDs sold in 2003. Now, if you were talking about, let's say, number of hybrid cars sold in California for several years, you put a little smart car icon here, you know, stack them up, and everyone likes that. It's kind of fun to do. But notice, you really do have to put a legend in that, because until you tell them that 1 CD icon is 1 million CDs, 100 million rather, they're not going to know it. You know, that's really not something that's intuitive. You've got to tell them that. So you've got to be really careful about how you do that. Now, the most important one is on page 534. It's a line graph. And line graphs are easy to make and actually can present a good deal of data. This one on 534 shows the number of bachelor's degrees earned by men and women for selected years, men in blue, women in red. And it goes from 1950 to 2010. Notice there's dots on there. This is very much like a connect the dot thing. They get their data, and the data would be from men and women for the different years, and those years differ by 10. So you plot them in, a little over 300,000 degrees in 1950. It goes all the way to 2000, where you have about a little over 500,000 degrees. Women started out at 100,000 in 1950, but went up to 700,000 in 2000. Okay? Then they connect the dots. Now, why connect the dots? This is an important thing. Drop down to the bottom of the page. They want to use this graph to estimate what's happening in 2010, which is even 4 years ago, but still, that's what they want. All right, what they do is take that line graph and extend the last section of the line over to 2010. For the men, it's a dashed line in blue. For the women, it's a dashed line in red. Now, what that's assuming is the trend will keep going at the same rate. Now, that doesn't always happen, but that is an assumption. That kind of thing started happening here at NPC in 2009. Okay? You can be sure they had to estimate how many people there would be in classes. In 2009, we exploded in classes. I mean, we used to worry about getting 15 people in a class. You know, that was our minimum number for a class. And that used to be a problem. In 2009, everything went to 30 and 40 people in a class. That's a huge explosion. So they've got a plan.